Good morning and welcome to the lecture number 24 of the course Water Resource Systems, Modeling Techniques and Analysis. Now, in the previous lecture, we went through the reservoir operation problem. We started with the standard operating policy. Recall that the standard operating policy deals with the release policy, whereby we meet the demands to the best extent possible from the amount of water available during the current time period. We do not look beyond, we just look at the current time period and look at the amount of water available, which is given by S plus Q, where S is the storage and Q is the inflow during the period. Compare it with the demand, and if we have adequate amount of water to meet the demand, you just meet the demand. And if you in the periods where you do not have adequate water, which means S plus Q is less than the demand, then you empty the reservoir, provide all the water to meet the demand and then empty the reservoir. That is the idea of the standard operating policy. Of course, you can also include the evaporation losses there. S plus Q minus E is what we look at in the standard operation. So, this is what we discussed. This is the phase in which the reservoir will be empty after you meet the demand. D is the demand and this is the S plus Q, which is the storage plus the reservoir inflow. During this period, it is a filling phase, because after you meet the demand, you still have some water left that will contribute to the filling of the storage reservoir. Beyond this point, there will be reservoir spills. That means, you have met the demand and at the end of the period, you still have excess water. That means, even after meeting the demand, you have excess water that goes as spill, because you can only store up to the capacity. Now, that is the standard operating policy. As I mentioned in the previous class, the standard operating policy is not an optimal policy, because you are not looking at other time periods. Then we discussed how to formulate an optimal reservoir operating policy for the same given data. The simplest form that we discussed was the LP formulation, linear programming problem formulation, where we are looking at maximization of the releases RT over all the time periods, which means essentially we are looking at maximizing the sum of the releases during all the time periods, subject to all the standard constraints. This is the continuity equation, and then we set RT less than or equal to DT. Because we are maximizing RT, you put an upper limit to make sure that RT approaches that upper limit. And then what is the upper limit? Upper limit is the demand itself. And these problems typically we are solving for one single objective, namely the water supply, where the demands are all known, and therefore, you would like to meet the demands to the best extent possible in all the time periods. Compare this with what we did in the standard operating policy. In the standard operation, you did not look at any other time periods when you are making a decision during a particular time period. Whereas, in the optimization, you arrive at a certain operating policy in terms of the releases to be met, as well as in terms of the storage to be maintained in the reservoir by looking at the entire year. So, typically we solve it for 1 year time horizon. By looking at the entire year, you will arrive at the optimal operating policy. That is the major difference, and therefore, the standard operating policy will not yield an optimal policy, whereas the optimization techniques that we have dealt with in this course can be used to obtain the optimal operating policy. Then we towards the end of the last lecture, I introduced a simple multi-reservoir system, and we are interested in obtaining the release policies for such multi-reservoir systems by looking not only across time periods, but also looking across space. That means, what is likely to happen at a particular reservoir because of the decisions that we take at some other reservoirs. So, we look at multiple reservoir systems, multi-reservoir systems as an integrated system, and then arrive at decisions, typically the optimal release policies at each of the reservoirs. Now, we will continue the discussion. So, for completeness, I will restate the problem and then we will formulate the mathematical problem. So, this is the system that we were considering. There are 3 reservoirs. I encourage you to also look at the previous lecture where I have discussed this in some detail, but I will just give the summary. There are 3 reservoirs here. Each of these 2 reservoirs, that is the reservoir 1 and reservoir 2. This is reservoir 1 and this is reservoir 2 and this is reservoir 3. The reservoir 1 receives its own inflow through its catchment, reservoir 2 receives its own inflow through its catchment, and the reservoir 3 receives not only the natural flows from this catchment, but also the controlled flows that are coming from reservoir 1 as well as from reservoir 2. Now, the fraction of the controlled flows that contribute to reservoir 3 from reservoir 1 is alpha 1. That means, alpha 1 R 1 T comes to reservoir 3 in period T. Similarly, alpha 2 R 2 T comes to reservoir 3 in period T. Typically, you can imagine this to be return flows from the irrigation, or you let some amount of water into the hydropower. After some losses, the hydropower tail race comes and joins the stream. So, there is certain amount that is lost or is already used from the releases that you make, and only the remaining amount of water comes and joins the stream and therefore, joins the downstream reservoir. Now, for this system now, we will look at how the formulation of a optimization problem by which we can derive release policies at all these 3 reservoirs in an integrated model. By which I mean, when you are deriving the reservoir operating policy at reservoir 1, you are also looking at the consequences of this reservoir policy on the reservoir 3. Similarly, consequences of operating policy at reservoir 2 on the operation of reservoir 3 itself. Now, we are considering that each of these reservoirs supplies serves the purposes of water supply, flood control and hydropower. So, at each of these reservoirs you have 3 purposes. Now, we introduce these terminologies B1T, B2T, I, B3T I refers to the reservoir, T refers to the time period and B1 refers to the unit net benefit corresponding to unit release. B2 refers to the net benefit corresponding to unit available flood freeboard, and B3 refers to the unit storage, that is the benefits associated with unit storage. Remember, we have said that the storage directly determines the hydropower. So, which means that the benefits associated with the hydropower may be in terms of the amount of power that you can generate is directly related to the storage itself. In reality, however, recall what I said last time, that it also depends on the release through the penstocks, because the power generated is proportional to Q into H. Q is the discharge and H is the head. Head is determined by the storage and Q is determined by the release policy. However, for this simple problem, we will just take it as storage, and therefore, we associate benefits associated with the storage, and these benefits can be typically hydropower generated at a particular reservoir storage in particular time period T. Then this is the continuity now, that is how the water is flowing from one reservoir to another reservoir, etc. Then for the flood control, we will specify a minimum buffer storage to be available in each of these reservoirs 1, 2 and 3 during the flood season, which means we will say that there must be a free storage space available at reservoir I, and that we specify as F min of I. This is the flood freeboard to be made available at reservoir I during the flood season. Then the release that we are making from each of these reservoirs is limited by the canal capacity itself or the river capacity and so on. So, you may put a higher bound on the release that is to be made from the reservoir. So, these are the conditions. One is that you want to meet the hydropower to the best extent possible, you want to maximize the power that is generated. You would like to at the same time maintain the flood freeboard to absorb the flood waters, and you would also like to make sure that your releases are such that they do not exceed a maximum value. This is the problem, and then you also have the net benefits associated. As I keep repeating, it need not be just the economic monetary returns, but it may be in terms of the physical outputs that you may get, in terms of crop yield, in terms of the hydropower that is generated, in terms of the the flood control volume that you could achieve, or the flood control that you could achieve, and so on. This problem now we will formulate as a simple linear programming problem and look at various terms there and various constraints. This is just similar to the single reservoir problem, except that we are, while writing the continuity, we are looking at the continuity of the flow from upstream or at any particular location. So, when we are writing the continuity at reservoir 2, for example, the reservoir 2 does not have any control structure upstream of it, and therefore, the natural flow that comes from the catchment itself is the inflow to this. Whereas, when you come to reservoir 3, it has the natural inflow Q3 plus the controlled flow coming from reservoir 1, which is alpha 1 into R1 t in time period t, and the controlled flow that is coming from reservoir 2, which is alpha 2 R2 t. So, you just look at the continuity, formulate the continuity equation at each of these reservoirs, those become constraints, and you formulate the objective function. Now, the objective function for this is that you are looking at maximization of the net returns out of this reservoir policy, operating policy. And we have defined at reservoir I, where I is equal to 1 to 3, the net returns that you accrue out of releases, out of maintaining a flood control storage, and out of maintaining a particular storage. So, let us see how we formulate this. Now, for this example, now you understand that the storage at any particular time, and we refer to the storage ST as the storage at the beginning of the time period. So, this is the time period T, and this is the storage at the beginning of time period T. Now, this storage must be always less than the capacity K. Further, this is the freeboard that we are talking about. That means, if you have a storage of ST and the capacity is K, the associated freeboard that you have for absorbing the floods is K minus ST. And then what we do is, for this example, we will say that the B1 T I, this I refers to the reservoir. We are assuming that at all the reservoirs, the constants B T remain the same. So, this is for release and this is for storage. Let me just take this B2 T is for flood freeboard and this one is for hydropower or the reservoir storage itself. So, we take out the superscript I here to indicate that these remain the same for all each of the reservoirs. Now, of course, in a general form you can also include I, but let us understand the formulation for a simplistic problem first. And now, we will look at how we formulate the objective function. You are looking at 1 year time horizon, which means T is equal to 1, 2, 3, etc. There are several time periods. If you are looking at monthly time periods, you may have 12 time periods. If you are looking at seasonal time periods, you may have 2 or 3. For example, you may have a monsoon season, non-monsoon season, or you may have a summer, monsoon and winter season, and so on. So, your time t here depends on the time horizon and the intra-seasonal periods for which you would like to make the decisions. If you are specifically interested only in irrigation and hydropower, you may still reduce the time period to 10 days, and if you want to operate it specifically mainly for flood control, your time periods can be even so smaller, let us say 1 day time period, 6 hours time periods and so on. Now, these details or these kind of sophistication we can include when we are going for real time operation. So, let us look at how we determine the reservoir operating policy for this kind of system, looking at all the reservoirs together. We will formulate this as LP formulation. Just understand these terms correctly. We have T time periods. So, this is the last time period in the year or the number of time periods. Number of time periods in the year. So, if you are looking at monthly time periods, T will be 12, and this is number of reservoirs, I is equal to 1, 2, 3. So, all you are doing is across time periods, across space over all the reservoirs, you are summing up the net returns that you get from the reservoir release policies. So, at the reservoir I, you are making a release of RTI. I is reservoir number and T is the time period, R is a release. And associated with the release, you get a benefit of BT1. We have removed the superscript I for the benefits. We are assuming that the benefits remain the same across all the reservoirs. Then you come to the second one, you understand this term correctly. This is the flood freeboard, flood volume or flood freeboard or flood storage available in time period T at reservoir I. This is K I is the capacity of reservoir I. So, if you have a storage ST in reservoir I, you have the flood freeboard available of Ki minus STI, and associated with this flood freeboard, you have a return of B2T per unit storage that is made available, and therefore, you multiply this B2T into I. Then the storage at the reservoir I is SIT, and this determines the hydropower. And associated with the unit storage, you have a benefit of BT3 in time period T. So, you are summing over time periods and you are summing it over all the reservoirs. So, this is how you formulate the objective function. I repeat, the objective function as formulated here is the sum of the returns that you get out of the releases that are made from each of these reservoirs 1, 2 and 3, and the flood freeboard that you have made available in each of these reservoirs in time period T, and also the hydropower that you are generating, which is directly related to the storage in each of these reservoirs. So, this gives this objective function as written here gives the net benefits across time periods within a year, that means over all the time periods within a year, over all the reservoirs together. So, that is a lumped objective function that we are talking about, and in achieving this, that is in achieving the maximum returns, we need to satisfy all the constraints, and specifically the flow of water from one point to another point is what we have to account for, and that is given by the storage continuity equations. The storage continuity equations we write for reservoir 1 and reservoir 2 together, because they do not have any control structure upstream of it, and therefore, you write for these two together. So, we will write first for reservoir number 1 and 2. For time period T, we write for reservoir number 1 and 2 together, because they do not have upstream control structures here. So, this will be a straightforward continuity equation, starting with a storage SIT plus QIT minus evaporation losses minus the release that you have made at reservoir I, and this is the spill or the overflow. So, this is overflow or spill in time period t. When you come to reservoir 3, I is equal to 3, you have to account for what is coming from the upstream, alpha 1 R1 and alpha 2 R2. These are the terms that you include here. This is the flow that is coming from upstream reservoirs. And this is SIT plus QIT, that is the storage in the reservoir number 3 and the inflow that is coming to reservoir 3. Remember, this QIT is because of the natural flow contributed by the catchment, free catchment. So, this is Q3T, that is the intermediate catchment between the reservoir 2 and 3 as well as reservoir 1 and 3 and the additional catchment that you may have. So, this is how you write the continuity for reservoir number 3. And of course, all other constraints that we have looked at, namely that the storage must be less than the capacity, and look at this constraint specifically. We write this because you want to maintain a minimum flood freeboard or flood storage, and Ki minus SIT, SIT is the storage. Look at this figure, SIT at particular reservoir I is the storage and K is the capacity. So, this becomes the flood freeboard. We would like to maintain this above a certain limit, which means that we specify a minimum flood freeboard to be provided, and then say that in each of these time periods, this term here must be greater than the minimum flood freeboard. For all the reservoirs I is equal to 1 to 3, we say for all t belonging to the flood season. Let us say that you are talking about a monthly operation in a monsoon country like ours, and you may have periods such as August, September, October as flood periods. So, you may specify this minimum flood storage only for those periods, and for all the remaining periods you would like to have the storage as high as possible, because the storage has benefits associated with the hydropower generation as well as for water supply, and therefore, you may want to have as high a storage as possible. So, you may put these minimum conditions only for the flood season, and for all the remaining seasons you may put this as 0. And this is the condition that we specify, which restricts the release that you make will be limited to, which restricts the release to the maximum capacity of the canal itself or the river itself. So, this is a maximum release constraint, and all other constraints are similar to what we have done earlier. So, this is a linear programming problem, because the BTs are known here, this is capacity which is known, and therefore, these are linear functions of the decision variables R and S. R is the release, S is the storage. When you solve this, you are leaving the boundary conditions open, in the sense that you are not specifying the storage either at the beginning of the time period at any of these reservoirs, or at the end of the year at any of these reservoirs. Leaving everything free, you are looking for the optimal combinations of the storages at each of these reservoirs as well as the releases, and that is what you would get when you solve this example. Now, in this general form, you can add several details as you progress. So, we will just solve a simple example using this model, and then see how you can add keep on adding details. For example, we said that the hydropower that is generated is a function of storage, and therefore, we associated the B3T with SIT itself. But you can also add to the hydropower the discharge that is going through the penstock, and develop the hydropower returns in terms of the discharge as well as the storage that defines the head. And to relate the storage with the head, you can also use the area capacity elevation relationships as we have discussed earlier, and then include those details here. Then you can also add other details corresponding to this alpha 1 and alpha 2, which we have taken as constants. They may be varying with respect to time, because if the alpha water that is coming from this reservoir is in fact irrigation return flows, that can be time varying. Similarly, if it is during the flood season, to maintain certain amount of flood storage, you may want to make additional releases, your alpha 1 can be different, and so on. So, many physical details of the system can be incorporated into this model to the desired extent. Obviously, the model will start becoming more complex as you add more and more details. However, the principle remains the same. So, these are all explained now. So, this is for completeness sake, I have given all the details here, all the definitions. The spill here overflow that we have included in the continuity equation may create some problem when you are solving the problem, because solving the this particular optimization model, because of the continuity equation. So, you may have several continuity equations. In this particular case, we may take 3 or 4 for demonstration, but in general you may have 12 time periods at least associated with the months, 12 months, and you may have not 3, but 14 or 15 reservoirs, and therefore, the number of equality constraints, including the overflows as decision variables related to the storage as well as the release, will be large. The number of equality constraints will be large, and therefore, in general, when whatever algorithm that you use for linear programming may fail to give a feasible solution. In such a situation, you may have to use the integer variables, as I have explained in the last class, and then account for the spills. Now, all these details are already explained. So, we will just look at how we solve this problem for a 3 reservoir problem. If you have another reservoir, let us say that from 3rd reservoir you are also going to downstream and then putting another reservoir here, and then to this reservoir there is another reservoir that is contributing. Let us say that you have this kind of a reservoir coming here. So, instead of 3, if you have 5 or 6 or 14 or any number of n number of reservoirs, the model structure remains the same as I just explained, except that you will keep looking at each of the reservoir and then add constraints associated with that, taking into account the continuity of the flow. Let us say you added one more reservoir here, you just write the continuity for this separately if there is no upstream control structure here, and then this contributes to the downstream reservoir, and R3T is coming from here. So, you add these two and put a continuity equation for this, and so on. Also, at each of these reservoirs you may have different objectives. This may be only for flood control, whereas this may be for flood control and hydropower together, and so on. So, all of these kind of specific systems details can be incorporated in the general model structure that I just showed, by accounting for the coefficients that we have used, the net benefit coefficients that I have shown here, and so on, and by rewriting the continuity equations, taking into account the continuity of the flow, from where it is coming, where it is getting added, how much of it is being extracted, how much of it is being lost, what is the kind of overflows or the spills that are occurring at each of these reservoirs, and so on. So, you are just maintaining the mass balance at each of these node points and then writing the constraints. So, the structure of the model remains the same irrespective of whether you have 3 reservoirs, 4 reservoirs, n number of reservoirs. We will just take a simple example with 3 reservoir systems, so that you understand the problem correctly. Now, this is the same configuration of the 3 reservoirs. So, essentially I am looking at these 3 reservoirs now. We will just take out these. So, this is a system that I am now considering, and for this system we will use some data. You have 3 reservoirs 1, 2 and 3. There are 3 time periods 1, 2 and 3. The inflow during each of these 3 time periods for each of the reservoirs is given in some units, volume units 25, 10 and 15. K is the capacity of the reservoir I. So, first reservoir number 1 has a capacity of 10 and so on 15, 20. The F min is the minimum flood freeboard that you need to maintain in terms of the volume units in each of the 3 time periods at each of these reservoirs. So, in time period t is equal to 1, you would like to maintain a minimum of 3 units of flood freeboard, and that is how this data is given. The B1 star that is shown here is the net benefit associated with the releases. At reservoir 1 it is 50, at reservoir 2 it is 60, at reservoir 3 it is 70 and so on. The B2 star is associated with the F min, that means the flood freeboard that you are providing, and the B3 star is associated with the storage. Now, these terms are the same as what I have used here, except that I am taking out the T here for in the example problem to indicate that the net benefits remain the same across all time periods. So, I am simply putting it as B1 star, B2 star and B3 star. And further we use alpha 1 as 0.2 and alpha 2 as 0.3, which means the fraction of the release that joins the downstream reservoir from the reservoir number 1 is 0.2 and this is 0.3. Okay, we will solve this problem. We will again rewrite the problem for t is equal to 1 to 3. There are 3 number of time periods. There are 3 number of reservoirs, and this B1t and B2t etc. are in fact B1 star and B2 star. So, I can write this as B1 star and this as B2 star and this as B3 star, essentially to indicate that across all time periods the coefficients remain the same. And we write the continuity equation. I just explained this for I is equal to 1 and 2 and also for I is equal to 1, I is equal to 3, which receives contribution from the upstream reservoirs. We write this constraint here. For t is equal to 1, 2 and 3, we have specified what is the minimum flood freeboard that needs to be maintained, and the flood freeboard at reservoir I in period t is simply K I, which is the capacity of the reservoir, minus SIT, which is the storage at the beginning of the time period t at reservoir I, and this should be greater than or equal to F min of I, and F min of I in each of these time periods is given. So, for completeness sake, we can also write this as F min t of I for t belonging to the flood season. That means, for each of these time periods in the flood season, you may have different F min specified as data. You imagine for example, a large system like a Narmada reservoir system, where you may have 14 or 15 reservoirs, and at each of these reservoirs you may specify a different flood freeboard during different time periods. Let us say in July you may specify something at let us say Bargi reservoir, and then at Narmada Sagar reservoir you may specify some other freeboard in July, but in August these two values can be different and so on. So, in general you can include this as F min t, which varies from time period to time period at the reservoir I for t belonging to flood season, we may say, and for t not belonging to flood season, this can be just 0. So, this is the model that we will solve for the example given earlier. What is the data that will be necessary here? The flows at each of these reservoirs, this is the inflow, this should be given. The evaporation rates may be specified. If you are ignoring the evaporation, then this term does not exist, and then you have to specify the storage capacities you have to specify the F min I. So, all of this data is given. So, the inflow is given at all the reservoirs for all the time periods. The storage capacities are given at all the reservoirs. You have specified the minimum storage, minimum flood control storage at each of these reservoirs for each of the time periods, and of course, the benefit functions. And the alpha 1 and alpha 2, which are the fractions of the releases from the upstream reservoirs that join the downstream reservoir. So, that is also specified here. This is the LP problem because the objective function is linear and all the constraints are linear. So, you can use a linear programming software and then solve this problem. Now, I am giving you here the code for the Lingo software, which, as I mentioned in the previous class, you can use it freely for educational purposes with limited number of constraints, limited number of variables and so on. So, this is the code I have explained earlier how to write, how to use the Lingo for single reservoir. We only extend it to multiple reservoirs. I do not want to spend too much time on this. Let us go further. So, we can use the continuity equations for time periods 1 to 2, and then your t plus 1 at the end of the time period becomes, let us say you have 3 time periods, the t plus 1 at the end of third time period becomes 4, and that you can account for in defining your continuity from one time period to another time period. So, this is a simple code, I will not go into the details of this. All we are doing is rewrite the constraints in the form of using the for loops and so on. And this is the data that we specify at each of these reservoirs. Because F min would have been defined as an array here, you would have defined F min as an array consisting of reservoir as well as the time period. You will write F min for each of the reservoirs for each of the time periods. So, this is the format. The syntax and other things of Lingo can be read from a manual. So, this is just a simple maybe about 15-20 statements of the Lingo problem. Remember here, irrespective of your number of reservoirs, number of time periods, etc., this program remains the same. That means, as your number of reservoirs increases, perhaps you may structure it slightly better, so that the continuity equation is written in a more general form. I have used it only because it is only 3 reservoir problems. So, I have used it slightly inelegant way of writing it, but you can make it more general, so that the problem can be solved for any number of reservoirs for any number of time periods. When you solve this, as I mentioned, you should get a reservoir operating policy, which means you should get the optimal storages to be maintained at the reservoirs and the associated optimal releases from each of the reservoirs, such that together something good happens to the system in terms of the best objective function that you get and so on. So, you will get the solution like this. You will get the storages to be maintained at each of the reservoir during each of these time periods. Remember, ST is the storage at the beginning of the time period. And similarly, at reservoir 2, the storage to be maintained, at reservoir 3, storage to be maintained and so on, and the associated releases and the associated flood free board. This is the flood free board. So, this defines the optimal policy. That means, at period number 2, let us say at reservoir number 1, you maintain a storage of 8, and then during the period 2, you make a release of 15, and then you end up with certain storage at the end of the period. Let us say 8 is your reservoir storage at the beginning of time period t is equal to 2, and then you have an inflow of 30. So, 8 plus 30 is 38, and you make a release of 15. So, 38 minus 15, that will be the storage at the beginning of next time period. You are looking at reservoir 1, I am sorry. So, at reservoir 1, you look at the flow during the time period t is equal to 2, which is 10. So, you have time period t is equal to 2, 8 plus 10, which is the storage plus inflow, and minus you make a release of 15, and you will end up with a storage of 3, that is this 3. So, the storage continuity, that is the mass balance, has to be maintained even in the optimal solution, and in general when you have large number of constraints, large number of reservoirs and so on, it is better to put a check on the final optimal solution that you obtain to ensure that the mass balance is in fact maintained in the optimal solution. Why this is important is because of the overflows. Overflows in general as equality constraints cause some difficulty in large linear programming problems. So, you must be alert to the situation that the optimal solutions that you obtain finally may have overflows occurring even when the storages are not at the capacity. So, the overflows must be non-zero only when the reservoir has reached the capacity, and that you must be you must make sure. At the reservoir 3, when you are checking for the continuity, you must make sure that you use the alpha 1 and alpha 2, because the reservoir 3 is also receiving water from upstream reservoirs. So, that fraction has to be accounted for when you are looking at, when you are checking for the mass balance at reservoir number 3. Okay. So, to summarize what we did just now is to arrive at optimal operating policies for multiple reservoir systems, multi-reservoir systems, where the decision that you make at one particular reservoir is going to affect the decisions at other reservoirs, typically the downstream reservoirs, or typically the reservoirs to which this particular reservoir is connected. And you are then looking at the integrated decision, integrated policy of how to operate the reservoir across time periods, such that it is part of a larger system in which several other reservoirs are also located, and then you are looking at a comprehensive objective function or an aggregated objective function for the entire system together, while at the same time maintaining the particular objectives of individual reservoirs. So, individual reservoirs may have their own priorities. For example, flood control may be a higher priority at a particular reservoir. You assign the associated coefficients there, the B star that I use there can be different for different reservoirs, can be different for different time periods, can be different for different objective functions. So, in general, when you have large systems, keep in mind a system like Narmada Sagar system, Narmada system, where you may have 14 or 15 major reservoirs apart from a large number of minor reservoirs. You may have different objectives to be satisfied at each of these individual reservoirs. At the same time, you may want to have a large systems viewpoint and then want to maximize or want to optimize something for the entire system together in an integrated way. And that is where we formulate models like this, optimization models like this, and arrive at optimal operating policies at each of the reservoirs, such that the policies are linked together across each of the time periods. This was using the linear programming. Recall that in one of the earlier lectures, I also introduced the dynamic programming for reservoir operation. What we did there was that for 1 year period, and the specific example that I took, numerical example, consisted of 4 time periods in a year. Maybe you refer to lecture number 16 and 17. What we did there was that we defined the reservoir operating policy as a set of sequential decisions to be taken based on the state of the system at that particular time. So, the sequential decisions as a function of the state of the system, and the state of the system in that particular example that I discussed was in fact the storage. Given the storage at the reservoir, how do we operate in a sequential manner such that at the end of the time horizon, and typically the time horizon is 1 year, the objective function is maximized. So, whenever we are talking about sequential decisions, the dynamic programming is much more elegant, much more handy compared to the linear programming problems. So, we will now revisit the dynamic programming and pose the problem slightly differently than what we did in the earlier case where we dealt with dynamic programming, and talk about what is called as the steady state policy or the stationary policy. We say a policy is steady state when you keep on applying the policy over and over again across time periods over many years, you get the same returns, maybe in terms of the hydropower, maybe in terms of the flood control, maybe in terms of the agriculture produce and so on. You keep getting the same returns as you apply this particular policy, which is a steady state policy, over a long period of time, and that is the intuitive understanding of the steady state policy. Typically, to derive the steady state policy, the dynamic programming is more well suited, because you can solve this problem over a large number of years. Let us say that you solve this problem of reservoir operation for 5 years, 10 years, 15 years, 20 years and so on. And as you get the steady state policy, how to get the steady state, I will presently discuss. As you apply the steady state policy over a long period of time, the net returns that you get every year will remain the same, and the policy also converges to a certain steady state policy, which you can keep on applying based on the state of the system. And this is the problem that we discuss now. So, this is either called as a stationary policy or the steady state policy, because you do not alter the policy. Once you derive the policy, by policy you recall what I mean is the decision on the releases to be made at each of these reservoirs for a given state of the system, and the state of the system typically is defined by the storage and the inflow together. And as I mentioned earlier, you can keep on adding more and more sophistications to the problem in terms of details regarding soil moisture, details regarding the rainfall and so on, to define the state of the system. So, the stationary policy derived using dynamic programming specifies the release as a function of storage in a period. In this particular case, we use the storage as the state variable. That is, the state of the system is defined by the storage. Now, the objective is to derive an operating policy which results in the maximized annual net returns. We will say benefit is also return. Do not always confuse the benefit with monetary benefits. Do not always relate the benefit with monetary returns. It is in general the returns that you get in terms of the hydropower, in terms of the irrigation, etc. So, keep the physical picture in mind when we are doing the optimization. Now, this in the long run is what is important. As I said, the steady state policy is typically applied over a long period of time, over 5 years, 10 years and so on, as against the policies that we discussed earlier, which were typically for 1 year. That means, you take a 1 year time horizon, optimize that and then use that for that particular year. Now, that need not be optimal in the sense of long term returns that you get, and therefore, we go for what are called as the steady state policies or the stationary policies. What we do in the in deriving the stationary policy is that we start from some time in future and proceed backwards, proceed in the backward direction. Now, you please revise what we did in the dynamic programming earlier. So, the last time period in a year is capital T. We start in the backward direction and these are the stages. So, n defines here, small n defines the stage in the dynamic programming. The Q1, Q2 etc. are the flows, inflows. So, you start the computations in the backward direction, each time taking one time period, and then next time you look at connection between this time period and this time period, next time you look at the connection between this time period and this time period, and so on. So, you progress in the backward direction until you are sure that the steady state has reached. So, this is some distant year in the future. Do not worry whether it is year number 20, year number 30 and so on. So, this distant year in the future, you are starting as the starting point and then progressing backwards. Keep doing the computations in the dynamic programming until you reach a steady state. By steady state, I mean the state where the annual returns will remain constant. The policy converges to a certain policy. That means there will not be any further changes as you keep on doing this again and again. This happens because your flows remain constant. This is a deterministic problem. You are not addressing any uncertainties associated with the flows. Therefore, the flows remain constant and you are solving it for year after year over the same intra-seasonal time periods. And therefore, after some time the policy in terms of the releases that you need to maintain converges to certain steady state values, steady state value. So, that is what we call as steady state policy. Now, there are certain features of this steady state policy that we must understand. You go to maybe lecture number 16 or lecture number 17, where I discuss the dynamic programming algorithm for arriving at the reservoir operating policy for a year. Now, there we applied a boundary condition saying that my storage at the beginning of the first time period was a specified value. Let us say in that example we took S1 to be equal to 0. However, when we are deriving the steady state policy, you do not apply any such conditions that either at the beginning or at the end. Leave everything free and let the algorithm choose what are the best storages to be maintained, or in this particular case we may say that if the storage is in fact the state of the system, for a given state of the system, what is the optimal route that you need to take. So, we do not specify any boundary conditions, that is a first condition. Then we use two indices here, one is n and another is t, much the same way as we did in the dynamic programming earlier. The n keeps the track of the progress of computations. So, n is the stage and keeps on increasing. So, n is equal to 1, 2, 3 etcetera, 12, 13, 14, 15 and so on, it keeps on increasing. The t there keeps track of the intra-season period corresponding to the stage. For example, n is equal to 1 corresponds to t is equal to 1, 2 corresponds to t is equal to 2. If you are doing it for a monthly time period, n is equal to 12 corresponds to t is equal to 12, n is equal to 13 corresponds to t is equal to 1, because a year consists of 12 time periods. So, t goes from 1 to 12, 1 to 12, 1 to 12 etcetera, whereas n keeps on increasing to keep track of the stage in the dynamic programming. And then we proceed in a backward direction typically for steady state operation, and then we carry out these computations until a steady state is reached. We will see how we identify the steady state in the dynamic programming algorithm. So, essentially then in today's class we started with the reservoir operation problem that we were discussing in the previous class. We introduced the multi reservoir systems where the continuity equations or the mass balance equations we write taking into account the controlled flows that come from the upstream reservoirs, and also taking into account the intermediate catchment flow at each of these reservoirs. The releases that we talked about from an upstream reservoir, only a part or a fraction of the release may actually add to the downstream reservoir, and this is what we account for in writing the continuity equation at the downstream reservoir. What I discussed through a 3 reservoir problem can be generalized to any n reservoir problem. At every reservoir you look at the conditions to be satisfied in so far as the mass balance at that particular reservoir is concerned, and also the specific objectives that that particular reservoir has to serve, and then integrate all of these in a single model. And we have looked at the linear programming model for multi-reservoir systems. Subsequently, when I discuss some applications, we will also see how we can simulate such reservoirs, such large and complex reservoir systems using Monte Carlo simulation techniques, and then generate several possible outputs, and then how do we screen these outputs through a linear programming problem and so on. Then towards the end of the lecture, then we solved a simple example of the 3 reservoir problems using the LP. Recall that in the last lecture I have introduced the software Lingo, which can be downloaded freely for educational purposes. You can use the small code that I have given for multi-reservoir systems and make it more general for any general reservoir system. So, towards the end I just introduced the concept of the steady state policy. We will continue our discussion on the steady state policy using the dynamic programming in the next lecture. Thank you for your attention.